Hi students, this is AJ sir. Let's study 9th standard ICSE Math, exercise 13B, Pythagoras Theorem. Also, to enroll for my online lectures or online test series, email me. Check the description for more information. Mark the following sums as IMP: 8th, 12th and 14th. Now let's start with question number 2. An equilateral triangle is given. Each side is x and we have to find the altitude in terms of x. We had done a similar sum earlier. Each side would be x and we know that the altitude in an equilateral triangle and even in an isosceles triangle bisects the base. That means DC is half of x. Now in right angle triangle ADC, use the Pythagoras theorem. Substitute AC as x and DC as x upon 2 and solve. Take the square root to get the answer of AD, that is the altitude, in terms of x. Solve it. Question 4 has a few subparts, totally 4 subparts. So this is the given diagram and we are going to join an M as well. So I see a lot of right angled triangles, 1, NQM, NQR, PQM and PQR. So there are totally 4 right angled triangles and all 4 will be useful in this sum. In Roman number 1, the question is PM square plus RN square. That's the LHS side. So first find PM square and Rn square by using Pythagoras theorem in the respective right angled triangles. Then add the two statements to get this. But this isn't the RHS we wanted, although the LHS has been obtained. Now PQ is twice of NQ and QR is twice of QM. That's because it is mentioned in the question that M is the midpoint of QR and N is the midpoint of PQ. So on substituting these values, we get this finally, 5QM squared plus 5QN squared. Take 5 common. So in the RHS what we get is QM squared plus QN squared. If you look at the diagram, QM squared plus QN squared is NM squared because it's a right angle triangle NQM. So again we have to use the Pythagoras theorem here. So that's how we get Roman number 1 proved. Next, Roman number 2. We have to prove that 4 times PM squared is equal to something. So PM squared is in the LHS, so let's start with that. Now PM squared is PQ squared plus QM squared by Pythagoras theorem. It was already proved earlier. But QM, if you remember, is half of QR. Keep looking at the diagram. QM is half of QR because M was the midpoint of QR. Substituting that and then taking the LCM, we get what is asked in Roman number 2. Similarly, in Roman number 3 also, the LHS had Rn squared. So we start with that Pythagoras formula. Then we substitute Qn squared as PQ upon 2 the whole squared because N is the midpoint of PQ. And on opening the bracket, squaring numerator and denominator both and taking LCM, we get what is asked in Roman number 3. And finally, Roman number 4, we are going to add equations 4 and 5, which we had proved earlier, because that's the LHS we see in the question. And definitely by solving this, we will get the RHS required. So 4pq squared plus pq squared is 5. This also 5. 5 common. And if you look at the diagram, pq squared plus qr squared by Pythagoras theorem is indeed pr squared. Now in the sixth sum, there's a rectangle and we have to prove something. So in this diagram, we have the diagonals. The LHS was AC squared and BD squared. So definitely there will be two hypotenuses of two different triangles. So use Pythagoras theorem twice. And make sure you write Pythagoras theorem in every case, Roman number 1 and 2. Now there are many ways to solve this. I am taking triangles ABC and BDC. But when I add these two equations, I don't exactly get the RHS asked, because I'm getting a BC squared here. BC squared and BC squared, I'm getting it twice. Whereas the RHS of the question is a bit different. But BC is equal to DE, DA, opposite sides of a rectangle. So I can just substitute this and then I get the RHS of the question. The eighth question again is in a rectangle, but there is a point O anywhere in between. So here's a point O anywhere inside the rectangle, and we have to prove OB squared plus OD squared gives you OC squared plus OA squared. Now note that angle AOB is not 90 degrees, so I cannot use Pythagoras theorem in triangle AOB. Hence we will do a construction QP which passes through O and which is perpendicular to AB. That means it will be parallel to AD and CB. We will use Pythagoras theorem in this triangle and in this triangle first of all, because this triangle will give me OB squared value and this triangle will give me OD squared value, and we will add those two equations so that we get the LHS of the question, OB squared plus OD squared, and we get this. But this is not the RHS of the question. So what we'll do is this PB squared and DQ squared shall be replaced. Because if you see in the diagram, OP squared and PB squared belong to this triangle, whereas we would like to shift it to this one. So PB is equal to QC. Why? Opposite sides of a rectangle. Yes, PBCQ is a rectangle. How? Well, this is 90, this is 90, this is 90, so obviously it's a rectangle. Even APQD is a rectangle. So PB is equal to QC and even AP is equal to DQ. This is something I had written in the beginning itself because I knew it's going to be useful later. And now we will substitute these two with CQ and DQ and AP respectively. But how is that useful? You'll realize shortly. So after substituting, this is what I get. So again, LHS is what we wanted, but in the RHS, I'm going to club together CQ squared and OQ squared and OP squared plus AP squared. Because if you look at the diagram, CQ squared and OQ squared is nothing but OC squared by Pythagoras theorem. And OP squared plus AP squared will give you OP squared by Pythagoras theorem, which is what will give us the RHS required. So after substituting these two with OC squared and OA squared respectively, we will get what is asked. Next, in the 10th sum, there are diagonals of a rhombus. Now we know that in a rhombus, diagonals are always perpendicular bisectors of each other. So with that property, we can prove this. Always mention the property being used. So first we'll use right angle triangle OAB. We'll use a Pythagoras theorem to find the value of AB squared. And we'll rearrange the terms to get OA squared because that is what is there in the LHS of the question, OA squared. Similarly, in triangle OCD, we'll get the value of OC squared. And then we add these two equations, so we get OA squared plus OC squared, which is the LHS as per the question. So now we'll have to solve the RHS to get it as per the question. Now we can substitute OB as half of BD, because we know O is a midpoint of the diagonal, as diagonals bisect each other. And even here OD, we can substitute it as half of BD. Same reason. Why are we doing this? Because in the question's RHS, if you notice, BD exists. So somehow we have to include BD out here. And also in the RHS of the question, there is AD. But we don't have any AD yet. That's fine. After all, AB and CD are same as AD because they are sides of a rhombus. So substitute this and this as AD, and these have been converted into BD. Solve further and you will get what is asked. Now in the 12th sum, there is an isosceles triangle and we have to prove this. We'll have to do a construction because there was no mention of a right angle triangle here. But we have to use Pythagoras Theorem in this sum. So construction is AP perpendicular to BD. Now remember, in an isosceles triangle, the altitude always bisects the base. That is, P is the midpoint of BC. That will be very useful in this sum. So first of all, we use Pythagoras Theorem in triangle APD. And we get the value of AD squared, because that is what is there in the LHS of the question. But the RHS is totally different from what is asked. So let's manipulate the RHS further. Now PD is PC plus CD. So we substitute that and we open the brackets, that is A squared plus B squared plus 2AB. We get this. This is still different from the RHS of the question. So next step, if you notice AP squared and PC squared, AP squared and PC squared actually belong to right angle triangle APC. So I can replace AP square plus PC square with AC square because that's the hypotenuse by Pythagoras theorem. And AC square is indeed there in the RHS of the question. So that's a wise move here. So instead of this bracket out here, I just substituted it as AC squared. What else? Well, I see CD is common here and here. So I took out CD common. And whatever is left is written in bracket. 1 CD is still left here, write it out here. Plus 2 PC is left, so write it out here. Keep looking at the RHS, keep looking. That will guide you to solve the sum ahead. What is the next step? You'll get the hint by looking at the question again and again. So I got LHS as per requirement. I got AC squared as well. I've got CD also, which is there in the RHS of the question. But only BD is left. BD entirely. Well, twice of PC is actually BC because P is the midpoint, as I explained earlier. So let me substitute 2PC as BC, and CD plus BC is indeed BD, and that's how we prove it. Now the 14th sum again has an isosceles triangle, and they ask us to prove this. Notice here AB is equal to AC entirely, and no need for construction. They have already told us to construct BD perpendicular to AC. First, let's use Pythagoras theorem in triangle BDA to get the value of BD squared, which is what is given in the LHS of the question. Now similarly, you could use Pythagoras theorem in this triangle also to get the value of CD squared, and then you can subtract it and solve ahead to somehow get this answer. You can attempt that method, but here I'm just going to use this equation and solve it further to arrive at this conclusion. First of all, BD squared is AB squared minus AD squared. Fine. Now we know that AB is equal to AC. So replace AB by AC. Why? Because now AC is actually AD plus DC. And in the question, if you see, the RHS has AD. as well as CD. So that's why we replaced it, and now we break it down into CD plus AD the whole squared. Then use the formula A squared plus B squared plus 2AB. Interestingly, AD squared and AD squared gets cancelled, and you are left with this. And if you shift CD squared to the LHS, we get what is asked. So that's how you have to practice a lot and try out various methods to figure out every sum in Pythagoras theorem. Keep looking at the diagram and keep looking at the question, and that would be a good guide for you to be on the right path.